Okay. Good idea. Yeah, and that's done in some places, right? You actually and except the little catch is to make it numb, you have to give a smaller injection first. So that may pain. Sorry. Appears at multiple points. Okay, how do I completely eliminate the pain? Almost. No, these are all good ideas. I'm just. You have a spray that can numb the area. That's actually done, right? The people use cryo sprays where actually it temporarily freezes your thing and then numbs. Okay. What else? So see, we're already innovating here, right? Okay, there's one thing that nobody's talked about yet, which is, you remember, see, if a key doesn't go into a keyhole, what do? You jiggle it, right? You shake it a little bit, right? If it's not going, it's getting stuck. To make it go easier, you jiggle it a little bit, right? And apparently the mosquito also does this, which is why you feel the itch after the mosquito bites you, but you don't actually feel it biting you, right? Apparently it is actually vibrating its probe while it is inserting the probe into your skin. Okay? So again, just giving you examples of what other people's knowledge can help you solve, right? Lots of things. People invented a toothbrush with toothpaste in it because they realized that you have to carry a toothbrush and a toothpaste wherever you go, right? So why have two different devices, right? That's an innovation. And then I'll give you another one, more like a puzzle, and I'll answer it later so that everyone has a little time to think about it, right? Okay? Very simple crime. Okay, an oil tanker. An oil tanker was going from point A to point B. Okay, typical oil tanker. I mean, you've seen our Chennai metro water lorries, looked almost like that, right? It was going from point A to point B. It was filled at point A. Customer was at point B, so it was emptied at point B. Okay? And point A filled 10,000 liters. Point B filled. When point B emptied out, there was exactly 10 liters less. Okay, so obviously the driver was stealing something, right? So point B filled 10,000 and point B emptied 9,990, right? So the owner got upset. He said, okay, now this driver is stealing something. Driver isn't confessing. So let me go with the driver, right? So the owner supervised the filling. He calibrated his equipment at the filling point and at the other point, at both points, to make sure that they are doing exactly the same reading and there's no error between the equipment, right? He sat with the driver to make sure there's no funny business. The driver was not allowed to get off anywhere, right? And then at point B, customer took out all the oil from the tanker, 10 liters less. Yeah, so if you've read the story somewhere, don't give me the answer. Let's not spoil the fun, but let's innovate here, right? Yeah, sorry. You want some time or you want to see answers right now? Yeah, so that he calibrated, okay? So the measurement device at A and B were calibrated so that it matched exactly. Yeah, so that was also good ideas, but of course he checked all that, right? It was closely shut and... Sorry? No, the pipe volume was accounted for, right? Okay, assume temperature at point A is equal to temperature at point B, right? Oh, that's a very good idea. Well, it wasn't. The storage container, that's actually a wonderful idea. I didn't think about it. But assume the storage container is completely separate from the, yeah. Yeah, like what? Okay. Good, good, good. Yeah. Okay. Okay. So, you know how this was solved? That was the solution, by the way. What's your name? I haven't heard anyone give an answer to this problem before. So, it was as simple as that. What was happening is the tris thing that was applied was separate in space, right? So the filling was happening from the top. You always fill from the top. The emptying was happening from the bottom, right? So all you need to do, all the guy was doing is he had a rope and a bucket, and he hung the bucket from the inside ceiling of the tanker. So it's as simple as that. What was the difference between filling and emptying? The filling happens from the top, emptying happens from the bottom, right? So that was the key. That was what the guy was exploiting, right? So he just, when you fill it, the bucket would be filled. When you empty, the bucket will not empty. Okay? So just to give you an interesting example of what, okay, now if you look at what TRIZ is really doing, I'm just going to repeat myself a little here. It is trying to take a solution from some other implementation and trying to force you to apply that solution to your problem, right? So it's forcing you to work in a multidisciplinary way, right? It could be a solution where somebody, it could be a solution that applies to a mosquito that you use for keys, right? So TRIZ is inherently forcing you to be cross-disciplinary, correct? Agreed? You may not realize it when you're using it, but that's what it's really doing. What is the Indian word for multidisciplinary? In any language? Sorry? I can't hear you. I don't know what that word means, unfortunately. Okay, give me more suggestions. Multidisciplinary. Everything, you want everything. Melting pot. Masala. Right? That brings me to movies. Okay? What is it that we love about our movies? Okay, I'm going to come back to the topic, but before that I'll ask you a question, right? Let's say we all start up a business where we want to predict whether a movie is going to succeed or fail. Okay? It's going to be $1 million thing, right? Literally, movies use crores and crores, millions of dollars to make. So if somebody comes to you with a script or the actual movie, if you can take a look and predict whether the movie is going to succeed or fail, how will you do it? Indian movies. Let's keep to our home ground first, right? Yeah, okay, good. 6 songs, okay. Each 4.5 minutes, right? Okay. 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 So, 6 songs, emotion, action, comedy. There must be a happy ending. Okay. Anything else? Okay. Part of those 6 songs, right? Okay. Sorry? Suspense. Okay. Mystery, right? Okay. So you guys are telling me that you want masala movies, right? That's what you want. You want all of this in a single movie. But is that enough? So, okay, first criterion, are all these ingredients there in that movie, right? Because you've got to predict to your customer whether this is going to be a hit or a flop, right? What else? Cinematography, wonderful. Screenplay. Okay. Now, if you take a moment, just think back, the movies that you liked. Yeah, I'm just... A twist in the end, okay, good. Which happens more and more of late, right? Most of the movies these days have a twist in the end, so you can almost predict it, right? So, just to try and summarize this, to capture all this, we want all the masala elements, but you want to be good in at least a couple of those elements, right? It's very hard to have a movie which has all of this and is good in all of this, right? So look back at our historical trace of movies. 60s and 70s, it was about solid storyline and drama and acting and all that. 80s, it was about story with songs, right? I'm just trying to generalize, so don't pick on this, but 80s, it was the intersection of stories and songs, right? How the songs actually merged with stories. 90s, songs and cinematography, right? 90s was when I was in IIT, and that's when Roja came out. It was a big hit because songs and cinematography, right? Maybe a story also, right? So they found a beautiful intersection of songs and cinematography. And currently, everything, right? The audience has become more demanding now, right? So you need the right intersection of an action comedy or an action and comedy with songs and with cinematography, or action with special effects, right? So any kind of combination where you at least have a couple of strong elements, right? Agreed? Maybe you can use that to predict, right? How the intersection between these masala elements plays out is a good predictor of movie success, correct? I think that's what the voice of the customer is saying here, right? Agreed? So, what did Jackie Chan do? He mixed comedy and action, right? What did Life of Pi do? Came up with a new idea. It mixed special effects and some spirituality, right? So you can almost start to predict now what works and what doesn't, right? What did Mission Impossible do? Style and adventure, right? So, what I'm trying to say here is, there is a saying that innovation happens at the intersection of disciplines. Okay? So whenever two masala elements, two disciplines intersect, that's where innovation happens. And you can see that in many, many examples throughout technology, throughout any form of art, or look at restaurants, right? What are the successful restaurants these days? I mean, the ones that are doing fusion cuisines in an Indian way, right? So that's at the intersection of multiple disciplines that innovation is happening, that people are making money, right? And this is a saying that, I mean, it's not to say that in the individual disciplines innovation has dried out. I mean, that will still be there, but the higher chance of innovation is at the intersection of disciplines. So in your final year project, make sure you have people from other disciplines, right? Anybody has any examples of multidisciplinary innovation? My own field, I'll start, is a field called MEMS, Micro Electromechanical Systems. It came from the thought that why don't we apply semiconductor fabrication technology to mechanical systems, right? That was a classic example of an intersection of disciplines, where semiconductor technology allowed a printing technique to manufacture devices rather than a component and assembly technique, right? In mechanical engineering, you typically make individual components and you assemble them later. That's not the way semiconductor fabrication works, right? You print, you use photolithography, you print, and you make everything in one shot, right? What does that do? It allows you to print multiple things at the same time, right? So you can do extremely complex structures. You can reduce cost, which is the big deal, right? Because when you start printing, it lends itself to mass production versus individual components in assembly, right? So the classic example of multidisciplinary research. Anybody has any examples? Bioinformatics, yeah. My wife, who just sang a song, she teaches Indian classical music over Skype. Classic marriage of technology and art. Because today nobody wants to commute. There's a lot of traffic, right? I'm sure everyone has complained about traffic on Chennai roads or any other city in India. Anything else? Okay. I'm sure you guys can think of lots of examples, right? So today, moving forward, companies encourage people to be jack of all arts and master of at least one or two of those. Okay, that's what industry wants. We don't want people who only know one discipline anymore, right? That's required in some niche areas, but we want people who understand everything, right? We want people to be mechanical engineers, electrical engineers, material scientists, civil engineers, computer scientists, all in one, And you got to be good at least one or two of those, right? That's what works in the industry now. Okay, back to movies. I'll give you one of my favorite examples of something that which helped me innovate on a new product we're working on. It's not something I can describe in great detail because it is protected by some intellectual property, but on the surface, right? All of you know that there's a lot of research going on in batteries, right? Batteries and energy storage devices, right? It's the holy grail. Electric cars haven't taken off because battery technology is not up to the mark, right? People haven't yet put solar installations on their apartments because battery technology has not yet taken off, because they need to use power in the nights. They'll run their air conditioners in the night, right? You need huge amounts of energy storage, right? It's one of the biggest areas of research today, right? So that actually, believe it or not, gave us a very unique inspiration, right? We said, okay, now what would we do if we lived in the time of Newton? We lived in the time of Galileo. We lived in the time of Maxwell, right? Very interesting proposition, right? So this was a time, let's pick a time where people discovered charges and electrostatics and things like that, right? People were doing very, very basic experiments. All they knew was, okay, there's an electron that's negatively charged, and if you remove the electron, it's positively charged. And people were doing experiments inside glass jars and so on to prove that like charges repel and unlike charges attract at that level, right? And then after that, people started coming up with basic laws of electrostatics, and then it went on to time-varying things, and then it went on to electromagnetics and all of that afterwards. But if you were in that time, when all of this was just invented, what would you have done? Right? So we actually put ourselves in those shoes just as a fun thought experiment, right? Then we said, okay, now let's forget everything we learned, right? Because you learned so many things in textbooks, and then at some point you accept everything that you learned and you stop questioning the very fundamentals, right? You're always taught, don't question the first law of thermodynamics, don't question the second law of thermodynamics. It's good advice, but sometimes you have to, right? So that led us to ponder. Now, how do you store energy, right? So back to the energy storage problem. There are two ways to store energy. Batteries store them in the form of ions, and capacitors store them in the form of electrons, right? So we said, let's keep it simple. I don't even understand how a battery works, so I'm going to just keep it to capacitors, where you just simply have two pieces of metal and you have electrons sitting on those metals, right? And then so right at that level you stop, okay? Then you do a calculation and see how many electrons you can store in a piece of metal. It's incredible. A huge number of electrons in a metal, right? And if you actually calculate the total coulombs, if you can strip the metal of all those electrons, you can achieve some phenomenal energy storage densities, right? So, I mean, you can do a mental calculation if you like, but even in a very, very small volume of metal, the number of electrons is so huge. So it is orders of magnitude more than what even a supercapacitor can store today. Okay, so I'm going to leave you with that because I can't give you more detail, but that actually spawned a whole project. We're writing a very detailed proposal now and essentially finding a way, I mean we have a way, but to practically implement huge amounts of very, very simple electrons-based energy storage. No funny business with novel materials and batteries and so on. Electron-based energy storage in a very capacitor-like system. Okay, very simple at heart, but arising from the concept that there's no reason you can only store so much energy in a capacitor, right? Okay, that was just an inspiration. One thing I left out was the other half of that infinity that we talked about, right? So we talked about one half, not half, but one portion, where we talked about all the knowledge that exists in the world today and how we can actually not reinvent the wheel and try to innovate within that knowledge. So there are tools that help you do that. So there's the other part, right? Stuff that hasn't been invented yet. How do you actually access that, right? Everybody heard of Ramanujan? Yeah? One guy nodding his head back there. He was a mathematician from India. So that's something that we can't ignore. So there is a portion of that infinity that comes to you in a flash. And if you understand that infinity, what you can achieve potentially is you convert the signs of invention to the signs of discovery, right? Because once you understand it, it's not invention anymore. It's discovery, right? And this happened to people, including, I'll give you another anecdote. Einstein was interviewed by a French mathematician, and the mathematician asked him, so how do you come up with your theories? Where does it come from? Anybody knows what his answer was? Sorry? Imagination, yeah, okay, but yeah. They tried to get him to define what that imagination was. He was a scientist, right? So he's trying to define what it was. I'm going to read it out to you. I've written it down here. All he said, I mean, he gave a long answer, but the crux of it was, he said, conventional words or other signs have to be sought for laboriously only in a secondary stage. I'll read that again. Conventional words or other signs have to be sought for laboriously only in a secondary stage, right? So there is something that happens that reveals things to you in a flash, right? I mean, whether it is magic or whether it is science is a different question. So, what differentiates us from things that cannot innovate? So that's one question we need to ask ourselves to understand how to innovate, right? And what people normally call this is called consciousness. Consciousness is our awareness of ourselves, and that is a key thing that differentiates us from other things that cannot innovate. There's been a lot of research that has gone into finding out whether consciousness is something that can be simulated in a computer program. People have been unsuccessful to date. Whether you can make a computer program complex enough and make it aware of itself. Right, that is what consciousness is. People have tried to do it and they have not really succeeded so far. Whether it can happen in the future is still a question. But that is a big difference that demarcates what we do from what computers can do, right? So, and I'm going to keep this answer short and simple. You understood how to do the first part of innovation, right? So all the knowledge that exists today, how do you tap into that? The second part of innovation is how do you find something that's completely new out of the blue? And this basic simple answer is you go to your hostel room and stare at the ceiling. That's how it works. People close their eyes, they impart consciousness, they impart awareness to the entity that they are trying to innovate on. It basically comes to them. So I know it is not a clear answer, but that's how people do it. I'll give you some examples if you want. Before getting there, I just want to give you a little teaser, right? A very small story, and then I'll come back to this point. Just something you can think about. If you know the answer, keep it with you, right? So I'll pose it to you. It's a very, very basic, simple question. You don't need to, doesn't matter what kind of an engineer you are. This is a pre-JEE question, okay? All of you know what a capacitor is, right? And what are the parameters in a capacitor? You have capacitance, you have charge, you have voltage, right? So the charge is the product of capacitance and voltage, correct? Q is equal to C times V, correct? Okay? Simple? What is the energy stored in a capacitor? Can't hear you, sorry. Half CV squared, right? Half into capacitance into square of voltage, right? So I know Deepika knows the answer to this because we've spoken about this before, but okay. So Q, C, V. Q is C times V, okay? Half CV squared is the energy, that's it. There's no more equations in this, okay? So let's say you connect a capacitor C to a voltage source of voltage V. How much charge does it build up? C times V, right? Okay, so it builds up a charge Q equal to C times V. Okay, how much energy does it have? Half CV squared, right? Okay, now you simply disconnect this capacitor from the source. Now listen to me carefully. Disconnect this capacitor from the source and assuming the capacitor is holding its charge. Okay. Okay, so assume some ideal conditions where the capacitor is holding its charge. Now you have an exact replica of this capacitor, also of capacitance C. Okay, now you take this charged capacitor, the replica is as yet uncharged, okay, it has zero charge in it, and then you simply connect this one capacitor to the other capacitor. So what is the net charge? Yeah? What is the total charge? Total charge is conserved, right? I mean, the electrons can't disappear somewhere, right? So total charge is still Q, correct? And what is the charge on each capacitor? Q by 2. Agreed so far? So you have two capacitors that are exactly the same. One capacitor started with charge Q and you connected it to another one. So charge on each capacitor is Q by 2. Right? And the voltage is? What is the voltage? Voltage is also half, right? So the voltage on each capacitor is V by 2. Agreed? Okay, now what is the total energy in the system? Half of the original. Where did the energy go? So tell me in real quantitative engineering terms. So it's simple, right? As I said, it's a pre-JEE question. And I thought I knew everything in electrostatics, and somebody hit me with this problem. Okay, explain that. Okay. 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 Okay, explain that in a little more quantitative terms so that everybody understands. You are hitting the right point. Yeah. Okay. Okay, you're almost there. I just need you to crystallize that thought a little more. Okay, I'll finish the story, okay? And then we can give you the technical explanation. So what that guy told me was, assume you are the electron. Okay, you see, he said you become the electron. You're on this capacitor and you are trying to go to the other capacitor. Okay? And then in all this discussion, we haven't talked about resistance. Right? So we are assuming there is no resistance. Right? And so you're this electron, you're at this high voltage and you want to desperately go to the other capacitor of a zero voltage, right? So that you can equalize the voltage in both parts. And what prevents you from going there? There is no resistance, right? What prevents you? If nothing prevents you, you have to reach there instantaneously, right? Okay, so you have to, nature tells you that you can only reach in a finite time, right? So you cannot go to another place instantaneously. What is preventing you from getting there? You are the electron, right? Something is preventing you from getting there. Mass, okay. Something simpler than mass. We are not going to relativistic calculations here, but we are sticking with classical electrodynamics. Okay, you have to travel a distance, okay? In electrical terms, what is that called? It's called inductance. Okay, so what you said was correct. In electrical terms, any geometry has an inductance. So the fact that you have to travel a distance is what is impeding you from getting there, even though there is no resistance. Okay, and there is an inductance. Okay, and when you have an inductance and a capacitance, you have an oscillator. It may be a very high frequency oscillator because the inductance is very small, but you have an oscillator. So that's what's happening here. The electron is trying to get there. It is not able to. What is impeding it is inductance, because there is always inductance in the system, right? And the inductance capacitance oscillation works as an antenna. The energy dissipates. Okay. Hopefully this was a little bit of an eye opener, right?